Chapter 5, Tactical Navigation with Whiskers. Many types of robotic machinery rely on a variety of tactical switches. For example, a tactical switch may detect when a robot arm has encountered an object. The robot can be programmed to pick up the object and place it elsewhere. Factories use tactical switches to count objects on a production line and also for aligning objects during industrial processes. In all these instances, the switches provide input that dictates some other form of programmed output. The inputs are electronically monitored by the product, be it a robot or a calculator or a production line. Based on the state of the switches, the robot arm grabs an object, or a calculator displays updates, or the factory production line reacts with motors and servos to guide products. In this chapter, you will build tactical switches called whiskers onto your Bobot and test them. You will then program the Bobot to monitor the state of these switches and to decide what to do when it encounters an obstacle. The end result will be autonomous navigation by touch. Okay, tactical navigation. The whiskers are so named because that is what these bumper switches look like, though some argue that they look more like antennae. At any rate, these whiskers are shown mounted on a Bobot in Figure 5.1. The whiskers give the Bobot the ability to sense the world around it through touch, much like the antennae on an ant or the whiskers on a cat. The activities in this chapter use the whiskers by themselves, but they can also be combined with other sensors you will learn about in later chapters to increase your Bobot's functionality. Okay, so here's the figure with the Bobot whiskers. You can see it's made out of this thin metal kind of coat hanger type material, and they stick out and kind of have these round circular ends. And you could put a bumper covering in front of those if you were able to mold the bumper. But yeah, the idea is that there's a left and right, and the whiskers will move back and ground out against one of these pins back here, and we'll be able to test that the input goes to ground. All right, so activity 1, building and testing the whiskers. Before moving on to programs that make the Bobot navigate based on what it can touch, it's essential to build a test and test whiskers first. This activity will guide you through building and testing the whiskers. All right, so we're going to gather the whisker hardware and disconnect the power from the board and servos. All right, here's the parts list. We have these 2 whisker antennas, a couple of washers, these spacers, let's see, these 3-pin headers, 2 3-pin headers, a couple of 10K ohm resistors and 220 ohm resistors, and these screws here. So we'll gather all those up first and start building it. Alright, so building the whiskers, remove the 2 front screws that hold your board on the standoffs. Okay, so yeah, the the microcontroller board, the basic stamp 2 board, or the homework board, we'll take 2 of the screws off of that, or the Board of Education board, and then we'll put our whiskers down and our washers, and then just screw them down. It looks like it's pretty simple. And we'll use the spacers first. So spacers, whiskers, washers, screws. And then we'll add in this circuit here. So, alright, it's going to be a little bit different on the 2 types of boards, the Board of Education and the homework board. 5, 4. Alright, so this is the schematic here. This is our switches here. They look like 2 open dots on a circuit. Those are connection points, those open dots. And then the switch is shown as being open here. It's a line that doesn't quite connect the 2 points. So we got the right whisker here and the left whisker on that side. And notice that when the switch is closed, it goes to ground or VSS. Remember this symbol here, the kind of 3 lines going down is a ground symbol, and VSS is the negative side of the battery or ground. Otherwise, when those switches are normally open, the current will flow from VDD through a 10K ohm resistor and into our pin that goes into our microcontroller. So pin 5 and 7, we'll be looking at the input, and normally it'll be showing a 1 because it'll be normally attached to VDD with this high ohm resistor, which will give us a weak path because it's got a lot of resistance on it. So it'll have a weak tie up to the positive voltage side. So we should see the 5 volts or a 1 on pin 7 and pin 5 normally. And then when something bumps into our whisker, the whisker will cause the switch to close, and then we will have ground here as if there's a hard line to ground. And the ground will have less resistance than the pull-up, so it'll go through the path of least resistance. We will see that the signal is grounded. So when it's hitting something and that whisker switch closes, we'll read a 0 from it because the path of least resistance will go to ground. So I hope that makes sense. Okay, make sure to adjust each whisker so that it is close to but not touching the 3-pin header. And it says leave about 1/8 of an inch. Okay. Alright, so this is for the new boards, the Board of Education, the people who have servos going directly into that black connector on their board. We have our 2 whiskers, a 3-pin header here. Okay, so on this one, apparently these screws go right into the ground plane that's in the middle of the board. Basically that ground plane is tied into VSS. This wire is really only here for the speaker. So it's really just the metal posts going into the metal in the middle of the board, which is tied into the ground plane. Everything's common ground, so that's how the grounding works. And then on pins 5 and 7, we have the 220 ohm resistors coming up here, and then the 10Ks going to high, the VDD, which is at positive 5 volts. So normally it'll go through the resistors, the 220 and the 10K up to VDD, and that's how we'll get our 1 or 5 volts. But when these whiskers, when the wire pushes back and it hits this post here, or that post there, that will cause the electricity to actually go down the whisker through the screw and into the common ground inside the board, and that'll cause it to ground out and become a 0 when we look at it. Okay, for those who had the What is a Microcontroller class and have the old style boards, it's a little bit different. However, pretty much it looks the same. It's just that our servos are over here. So again, we have the 220 ohm resistors and the 10K ohms going up into VDD. And it's the same with the whiskers here. So the whiskers, again, the ground goes right through the screw and the extra spacer and into the center of the board. You'll actually see around the hole there will be a little metal exposed for the ground plane that's in the middle of the board. And when this whisker pushes back into the 3-pin header, that's going to cause it to short circuit. That'll be the lower path. So what'll happen is when we read the input on 7 or 5, it would come through the 3-pin header. This would be touching, so it would travel down this whisker and into the screw in the middle of the board, so that would be sensing a 0. All right. Testing the whiskers. Take a second look at the whisker schematic. Each whisker is both a mechanical extension and the ground electrical connection of a normally open single pole, single throw switch. All right, so all what that means is that because these whiskers are kind of springy, and we are going to tighten them down with these screws, they aren't going to touch normally. They're not going to touch into this 3-pin header. They're only going to touch when there's some force pushing the whisker back. So they're not normally going to touch. So that just means it's normally open, and that's how it's shown in the diagram here. Right there. All right, so the reason the whiskers are connected to the ground is because the plate holes at the outer edge of the board are connected to VSS. So that's why I was saying when you take off the screws that are holding on the board, you'll see that there's a little bit of metal that those screws are going into, and that metal goes throughout the middle of the board and is actually connected into the VSS that's in our prototyping area and into the processor. It's the microcontroller itself. All right, and because the whisker's made of metal and the standoffs are made of metal, it all conducts that electricity. All right, the basic stamp can be programmed to detect when a whisker is pressed. I/O pins connected to each switch circuit monitor their voltage at the 10K pull-up resistor. So here's that 10K, so it's normally going this way. When a given whisker is not pressed, the voltage on the I/O pin is connected to the 5 volts. When a whisker is pressed, the I/O line is shorted to ground, so the I/O line sees 0 volts. And again, because it's 10K on the weak, they call that a weak pull-up, because it's 10K and there's no resistance this way, the path of least resistance will go that way. You can think of this when it's open as being very, very high resistance, so like a million ohms, and so it would go this way because 10,000 is less than a million. All right, all I/O pins default to input every time the PBasic program starts. This means that the I/O pins connected to the whiskers will function as inputs automatically. As an input, an I/O pin connected to a whisker circuit will cause it to input register to store a 1 if voltage 5 volts or the whisker is not pressed, or a 0 if the voltage is 0 volts, the whisker is pressed. This debug terminal can be used to display the values. The debug terminal can be used to display these values, yeah. How do you get the basic stamp to tell you whether it's reading a 1 or a 0? All right, because the circuit is connected to P7, this 1 or a 0 value will appear in a variable named in7. In7 is called an input register. Input register variables are built in and do not have to be declared in the beginning of the program. You can see that the value of this variable is you can see what the variable is storing by using the command debug bin1. The bin1 is a formatter that tells the debug terminal to display one binary digit, either a 1 or a 0. All right, I think we saw a different command that used a question mark on in7 before, but so we're going to use this binary 1 to mean either it's a 0 or a 1, which you would think a binary would just be good enough. I don't know why it has to be binary 1. But so it's debug binary 1 and then input 7. Okay, so again, looking inside of the basic stamp integrated circuit here, um, we see that this is normally open, so you can think of that as being like a really, really large resistance or no path whatsoever. So it would go through this 10K resistor to VDD, which is a high voltage, and that would cause the input on pin 7 to be switched to 1 to show the high. Okay, and then when the whisker is pressed, the switch is closed. And so because there's no resistance, this is now like a direct connection, as if there was a wire between, which, I mean, literally it is with a whisker. It'll be lower resistance than this 10K resistor. So the path for the signal will go, because of the path of least resistance, it'll go to ground again. And so that'll show up as a 0 inside on pin 7, so it would be switched to 0. Okay. This next example program is designed to test the whiskers to make sure they are functioning properly. By displaying the binary digits stored in P7 and P5 input registers in 7 and in 5, the program will show you whether the basic stamp detects contact with the whisker. When the value stored in a given input register is 1, the whisker is not pressed. When it is a 0, the whisker is pressed. Okay, so this is normally high, so we would normally see a 1, and then it's going to be 0 when it's being pressed. We call that an active low. So we know the switch is active when it's a low value. Okay, so here's the steps. Reconnect the power to your board, enter the program below, and then use the terminal. Alright, so the program, it just puts out a little header information about the whisker. It says whisker left and right, and then it just in a loop goes in, it prints out the value of pin 5 and pin 7 as binaries. So you'll see like 2 columns going down where it just says, 0 space 1, and it's going to do that I think 20 times a second. So this thing will scroll off almost immediately, and then you'll see these 2 columns filled with zeros and ones. Alright, yeah, so they'll look like this. P5 equals 0, P7 equals 1. And then what you'll do is you'll just push the whiskers back into those 3-pin headers to see the values changing. And that's how you'll test your whiskers. Alright, so yeah, activity 2, field testing the whiskers. Assume that you may have to test the whiskers at some later time away from a computer. Since the debug terminal won't be available, what can you do? One solution would be to program the basic stamp so that it sends an output that corresponds to the input signal it is receiving. This can be done with a pair of LED circuits and a program that turns the LEDs on and off based on the whisker inputs. I hope you get the idea. So basically you add a few LED circuits. One stands for the left whisker being active, and one stands for the right whisker being active. And when you see that in your program, you just turn it on. So I don't think we're gonna do that one. It's just more work, and I think we'll skip that. Activity 3, navigating with whiskers. In the previous activity, the basic stamp was programmed to detect whether a given whisker was pressed. In this activity, the basic stamp will be programmed to take advantage of this information to guide the Bobot. When the Bobot is rolling along and a whisker is pressed, it means that the Bobot bumped into something. A navigation program needs to take this input, decide what it means, and call a set of maneuvers that will make the Bobot back up from the obstacle, turn, and go in a different direction. Programming the Bobot to navigate based on whisker inputs. This next program makes the Bobot go forward until it encounters an obstacle. In this case, the Bobot knows when it encounters an obstacle by bumping into it with one or both of its whiskers. As soon as the obstacle is detected by the whiskers, the navigation routines and subroutines developed in Chapter 4 will make the Bobot back up and turn. Then the Bobot resumes forward motion until it bumps into another obstacle. In order to do that, the Bobot needs to be programmed to make decisions. PBasic has the command called an if-then statement that makes decisions. The syntax for the if-then statement is if, condition, then, otherwise else if, else, and then an end if at the end. The dot 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 means you can place a code block, one or more commands, between the key words. The next example program makes decisions based on the whisker inputs and then calls a subroutine to make the Bobot take an action. The subroutines are similar to the ones that you developed in Chapter 4. Here's how the if-then is used. Okay, so if input 5 is 0 and input 7 is 0, then that means that both whiskers detected an obstacle. Both whiskers are pushed in, grounding pins 5 and 7, so they're both 0. So what it's going to do is it's going to call the subroutine to back up. Then it's going to call the subroutine to turn left twice. So it's going to back up and turn a good ways to the left. Maybe do like a 180. All right. Otherwise, or else if input 5 shows a 0, that means only the left whisker was contacted, then it's going to back up and it's going to turn to the right. So, right, if it makes sense, right? If you see an obstacle on your left side only, you just back up and turn to the right. You don't have to turn all the way around. Okay. Otherwise, or else if pin 7 is 0, then it's going to back up and turn left. So, right, if the right whisker is being pressed, then we're just going to back up and turn to the left, or we're going to turn away from the obstacle. Otherwise, neither of the whiskers are being pressed. So in that case, we'll just go forward. And so that's the basic program, how it works. All we got to do is put that thing in a loop, and we should be basically done. So here's the example program. Roaming with whiskers, it's called. This program demonstrates one way of evaluating the whisker inputs and deciding which navigation subroutine to call using if-then. All right, reconnect your power to your board, enter and save the roaming with whiskers BS2. Try letting the Bobot roam when it contacts an obstacle in its path. It should back up, turn, and then roam in a new direction. So basically we can put this program in, run it, put it on the floor, and then we can do things like either put obstacles in there, or we can just push the whiskers with our hands in order to get it to change directions. So, yep, here we put that if, else, and if construct into a do loop so it does it forever. So again, here's our check to see if both whiskers are pressed, and it backs up and then it turns left twice. Here is the left whisker being contacted. It backs up and turns right. Right whisker backs up and turns left. Otherwise, no whiskers are being pushed, so it just goes forward. Okay, and here's our subroutines for forward, left, right, and back up. And those are basically our pulse out commands that we saw early in the class. All right, this is basically just an explanation for the program again. I have already kind of gone through it a couple times, so I don't think it needs any more. And I think that's probably going to be good for next week, if not 2 weeks. So we'll just leave it there.